Good evening. So, is my screen visible? Okay.
Yes, sir.
Okay. Okay. So I will just start. Last class, you were not there. So what I did is that I just started plasma. So I will just go through. I briefly started plasma physics. So I just will go through once again 5-10 minutes, and then I will start with today's class.
Okay, sir.
Okay, so yeah, so what is, first of all, I started with something called as plasma physics, where we are trying to study what plasma is. So first of all, why plasma? Because we are studying ionosphere. So basically, from ionosphere we came to plasma because we know that in our ionosphere there is constant supply of radiation coming from the sun, which is in turn photoionizing the neutral atoms, and an atom is splitting into, for example, some radiation is coming from the sun. Suppose you have some oxygen molecule, it will just split it into ions, and there is oxygen atom, you just split it into ion and electron. So ionosphere has a large amount of ions and electrons. So plasma is another form of state, just like a solid, liquid, and gaseous state of matter. Plasma is another state of matter which consists of charged particles like ions and electrons. So when you're trying to study the motion of particle in ionosphere, you need to consider ionosphere as a plasma, and then you need to know that how plasma physics, what is the dynamics inside the plasma physics, for example, motion, equation of motion of a particle, how would you write that in plasma. So if you do that, you will be able to understand the motions in ionosphere. So I started with the concept of d by sphere and d by length. So I will just go through them one by one, these lines. So basically, first of all, what is d by length? So in very easy terms, if I want to tell you, is that suppose you have a rectangular box like this, which contains plasma. Okay, that is, it has ions as well as negative electrons everywhere. It is filled with ions and electrons. So and then you put an external charge plus positive charge. Somehow you introduce this positive charge, which we call as test charge, into this plasma from outside, plus q. So what will happen is that since it is a positive charge, electrons would start due to Coulomb interaction, the electrons will start accumulating near this positive charge, and after a short time, for example after some time t, they will form a cloud of negative electron, will form a cloud around this positive test charge. So what is the significance of this spherical cloud is that the influence of the electric field or the potential which is created by this positive charge, which is this called Coulomb potential, 1 by 4 pi epsilon naught q by r, where r is the distance. So the effect of this Coulombic potential due to this test charge would be felt only up to a certain distance, for example, which is the radius of the sphere, and the radius of the sphere up to which the potential of the charge would be felt is called the d by length, or this sphere is called d by sphere. Outside this sphere, what will happen is that if suppose some electron is situated here, so this electron will not feel the attractive force from this positive test charge. So this is the significance. This happens only inside plasma, because if there was no plasma and we put a test charge in open space, then we know that if another charge would feel up due to this, it would set up a potential. Another charge will feel the Coulombic interaction, and the potential which is generated by this positive test charge is 1 by 4 pi epsilon naught q by r. So this potential tends to 0 only when r tends to infinity. When r tends to infinity, then it becomes 0. That is, the effect of this charge will be felt up to infinity if you put any test charge in vacuum or in just normal place. But if you introduce the same charge inside a plasma, then the dynamics is different. There is a particular length up to which is called the Debye length. Up to the Debye length, the charge would exert its influence, Coulombic potential. Outside that, the Coulombic attraction would not be felt by any other charge. So this is the significance of Debye length. So I was just trying to derive the expression for Debye length, and then I will derive the Debye potential. So for that, what I have done is that I have just taken a plasma and introduce a test charge plus q to the plasma. So due to this test charge, there would be a Coulombic potential at time t is equal to 0, which is q upon 4 pi epsilon naught r. But after some time, what will happen, that this negative electrons would start accumulating around this positive charge, and they will form a cloud. Okay. So first of all, why these negative charges are accumulating? Because of the fact that first fact is that we have introduced a positive charge. And the second fact is that since we know that the mass of electron is very, very less compared to the mass of ions, therefore the velocity of electrons is always greater than velocity of ions. This is because mass is less, so the velocity will be larger. Hence, we can treat that ions are at rest in comparison to electrons. When we compare the velocity of ions, it is very, very less than velocity of electrons. So inside plasma, we consider that electrons are at motion and ions are at rest. That's why these ions are accumulating, moving, and with certain velocity, and they're accumulating around this positive test charge. Okay. So what has happened is that one other property of plasma is that, which I forgot, that the total number of positive charge or the total number of negative charge is always equal to the total number of positive charge. So overall, plasma is neutral. Overall, plasma is neutral. As the total positive charge is equal to total negative charge. Negative charge is equal to total positive charge. However, when we put a test charge, then what happens is that inside this Debye sphere, you have a large amount of electrons. Okay. So there is some charge density happens. Some charge density occurs because of the fact that inside this Debye sphere, the number of electrons becomes greater than the number of ions, because we have introduced a positive test charge. So in a particular region inside the plasma, the concept of neutrality doesn't hold. That means there is certain amount of charge density which occurs inside this Debye sphere because of the fact that the number of electrons is greater than number of ions. So that leads to some charge density which is called rho. Now we know these equations from Maxwell equation. We know that divergence of electric field is given by rho by epsilon naught. Now rho is charge density, which can be further written as q times, that is charge, times this number density, that is number of electrons minus number of ions per unit area, and that in turn will give you the charge density actually. So we can just write this equation like this. This is within the sphere. Okay, this is within the Debye sphere. So now we also know that the electric field can be written as minus gradient of potential. This potential is your Coulombic potential, 1 by 4 pi epsilon naught q by r. Okay. So we can just substitute this into this equation. So we will get del square phi, minus sign will also come on the RHS, q times Ne minus Ni upon epsilon naught. And then in further, because electron is negatively charged, it can come E times Ne minus Ni epsilon naught. Okay. Now based on the thermodynamic equation and the Maxwell-Boltzmann theory, This is the distribution of how the electrons will be distributed. Don't need to go into details of this right now. You must have studied in thermodynamics. And this is how the electrons are distributed. And no n is equal to n naught times exponential of minus e by kVt, where kVt is the thermal energy of electron and this energy is the Coulombic energy of the electrons. Okay. Why thermal energy? Because we know that this plasma exists at certain temperature T, and if there is some particle which is existing at certain temperature T, it will have certain kinetic energy, half mv square, which will be equal to Boltzmann constant times T. For anything which is existing at certain temperature, it will have certain kinetic and thermal energy as well. So okay, now after this we come to this equation. So we will try to understand that how the expression of number density of electrons and ions are changing. Now since ions are at rest, so their concentration remain what is initial condition. Initially, if it is n naught number of ions, it will remain n naught. And electrons, since they are at motion, so their distribution will be given like this: n naught times exponential minus e by kVt. So what we'll do is now from 4 we can write fifth equation. This one, del square phi is equal to minus e. We have just rearranged, so ne minus ni becomes minus of ni minus ne upon epsilon naught. Now we just substituted the value from this two equations back into this, so we'll get ni is equal to n naught from here, and ne will be n naught times exponential of this term. Now what we'll do is that this is same only. I have just written this is Coulombic energy as I told, so Coulombic energy is minus charge times potential. So I just substituted it, so it will become plus of E phi, where E is the charge, phi is the Coulombic potential. Now one important assumption, and not assumption, it is fact, that the Coulombic energy is less than the thermal energy. Coulombic energy of an electron or ion is always less than thermal energy. So assuming this, E phi will be less than kVt. So when we do this, and when we just open this exponential, because we know exponential is what? Exponential of anything is 1 plus x square upon 2 factorial. This is obtained through binomial expansion. So we just use this and opened exponential of E phi by kVt. So it becomes 1 plus E phi upon kVt, plus higher order terms we neglected because of the fact E phi is very less than kVt. That means E phi by kVt will be very less than 1, and E phi by kVt square will be even more less than 1. So we are neglecting higher order terms. So higher terms we are neglecting is equal to 0, and then when we solve this, 1 will cancel. So finally we will get this expression: del square of phi is equal to E square times n naught upon epsilon naught kVt times phi, where E is your charge, which is value 1.6 into 10 to the power 19 coulomb. N naught is the density of the initial density of electrons. Epsilon is your permittivity, kV is Boltzmann constant, T is the temperature inside the device sphere. So further, this value, which can be written as 1 upon lambda d square, which I have written over here. So where this lambda d square is nothing but epsilon naught kVt upon no e square, and the square root of it will give you t by length. Okay, so this is basically the length up to which the effect of test charge would be felt. Outside the debye sphere, the effect of this test charge would not be felt, and that's why it's also called a shielding effect, because these electrons which form a cloud around this positive test charge, they shield this positive test charge. It's also called plasma shielding effect. So this is the typical length scale up to which the shielding effect is there. It depends upon the temperature of the plasma, directly proportional to the under root of temperature. These two are constant value. This is also constant. So your lambda d or your d by length is directly proportional to the under root of temperature, and it is inversely proportional to the charge density. These are important points regarding your d by length. Now I will just okay. So one thing, does it make physical? How to physically understand these two property? So suppose if your plasma is at a very high temperature, if your plasma has a very high temperature, that means its thermal energy will be very large. Okay, and if thermal energy will be very large, then these electrons which are forming cloud around this positive test charge, this cloud would not be formed very efficiently, or you can say that because of the fact that they will not move very close to the positive test charge, because see, there are two things. First is the Coulombic interaction, which is pulling these negative charges close to this positive charge, and other is thermal energy, which is moving this negative charge away from the positive charge. So if the temperature is very high and then your thermal energy will be very high, then your Debye sphere will be large, because this thermal energy will overcome the Coulombic attraction and the Debye sphere will be large. And another, so that's why it is directly proportional, and it is inversely proportional to the under root of density of the electrons, because if you have very large number of electrons, that means that if the density is very high, that means even at a very small space around this positive test charge, you will have sufficient amount of electrons which would be able to form a shield, because the density is very high. Per unit volume, large amount of electrons are present. So that's why in this case Debye sphere will be very small. Okay, so that's why these two conditions we can understand physically. Now I will just solve what is Debye potential. So Debye length, we have known what is Debye length expression and what is the physical significance of it. Is this clear? Debye length. It is basically the length scale up to which the effect of test charge is felt. Outside that limit, the test charge impact or its potential would not be felt by the particles. Okay, so now I will move to something, another topic, which is called potential. I'm just giving this name plasma potential, so phi r. So what is it? So we know that del square phi, we've already derived, is equal to phi upon lambda d square, where lambda d is the Debye length, and it is equal to what? It is equal to epsilon kBt upon Ne square. Epsilon kBt upon Ne square. Epsilon naught kBt upon n naught E square. This is Debye length. All units are in standard, so it is in meters. Okay. Now we also know that we can write in spherical polar coordinates. In spherical polar coordinates, we can write del square. This is basically Laplacian of potential. This del square is called Laplacian operator. So del square can be written as, in spherical polar coordinates, 1 upon r square d by dr. So spherical polar coordinates mean you have radial distance, theta and phi, your three coordinate system. Okay, del by del r square del phi upon del r plus write it as this, plus 1 upon r square sine theta del upon del theta sine theta del capital phi upon del theta plus 1 upon r square sine square theta del square phi upon del phi square. Okay, so this is your Laplacian operator in spherical polar coordinate. Now what is thing is that this Coulombic potential capital phi of r is independent, symmetric about, not independent, symmetric about theta and phi coordinate system. That means it doesn't vary across this theta and phi direction, is equal to 0 and is equal to 0. Okay, so all these terms which have derivative with respect to theta and with respect to phi will go. So what will remain is that del square is just will have radial dependence, which is del upon del r square del r phi upon del r. Okay, so using if is let's say this is 2, this is 1, so using 2 in 1, what we get is 1 upon r square del by del r square del upon del phi by del r is equal to phi upon lambda d square. This is equation 3. Now if you solve this differential equation, so what will get the second order differential equation, so what we'll get is the solution will be something like, if we solve it for potential, it will be 1 upon 4 pi epsilon naught q upon r into exponential of minus lambda d upon, sorry, minus r by lambda d, minus r by lambda d. So this is the Coulombic, we can say, potential inside the plasma, inside. This is general expression for the potential inside the plasma. So it has two terms. The first term is the general Coulombic term, or which Coulombic term, decay term I will write. Why decay? Because it varies as 1 by r. So with increase in r, it will decrease, the potential will decrease. And this is the exponential decay term. This is the exponential decay term. So basically there are two important terms in this Coulombic in this plasma potential. One is the Coulombic potential, Coulombic decay rate, another is the exponential decay term. Okay, so that's how we write the expression for the potential for created by any test charge which is placed inside the plasma. Okay, so it is not usual, it has an extra term which is this. This is the extra term which is coming, which is very important, because the significance of this term is, suppose on the x-axis you have radial distance, on the y-axis you have, so this is your r, this is your phi. Okay, so initially your potential will decay like this, suppose, and up to a length called lambda d, that is up to d by length. After d by length, it will start decaying exponentially, okay, to some point. So this is exponential decay. So the significance of this potential is that up to d by length, it will decay through Coulombic decay, like 1 by r. Outside it will decay as e to the power minus r by lambda d. Okay. So that is a difference. So how? So we can just divide this potential into two terms. So let us say that but r is 0. Let us take some cases. Case 1, r is 0, that is at the test charge itself. So when we put r is equal to 0, so your phi r will become, your exponential term will become what? This will become not exactly 0, but when your r tends to 0, I will put it later because you cannot reach exactly 0. When r tends to 0, your exponential term will tend to 1, and your Coulombic decay term, which I will write as suppose phi of c, where that is phi of c, this will go to infinity, right? Because there is 1 by r term. Okay, so the Coulombic potential will be very large, and the exponential term will equal to 1. So everything will be, so it will blow up, kind of blow up at the position of the charge itself. But case 2, when r increases, your Coulombic potential, which I write as phi of c, will start decreasing, and your exponential decay will also start decreasing, because both are decay. However, the rate of decay is different. One is exponential, one is 1 by r. Question is, what will happen when r, you keep on increasing r from 0 at d by length. When r is equal to lambda d, then your Coulombic potential phi c will become 1 upon 4 pi epsilon naught into 1 upon lambda d, and your exponential term will become what? E to the power minus 1. Okay, so this at r is equal to lambda d, this is what your potential will look like. And when r is equal to lambda, suppose r has become twice of lambda, so it is basically what? This is basically phi of lambda d upon e, right? Coulombic potential of at lambda d, because Coulombic potential is what? 1 upon 4 pi epsilon naught r, q by r. So if you just replace r with lambda d, it will become this. Yeah, so there will be a q term also. Okay. Now suppose your r becomes twice of lambda d. So in this case, this is not Coulombic, this is, I will write total potential. So total potential will become Coulombic potential at lambda d, I think 2 lambda d will be there, upon e square. Now e is what? E is your 2 point something, I don't remember, 7 1 something. So if you keep on increasing at distance, your Coulombic potential will keep on decreasing exponentially, because you are doing square e cube e4, so it start decreasing, rate of decrease becomes steeper. That's why till lambda d, when r is equal to lambda d, it follows the Coulombic potential, and after lambda d it starts decaying exponentially. E square, e cube will come, and e4 will come, so there will be exponential decay. So that's why we get this kind of term. So up to what you can remember is that inside a plasma, if you put a test charge up to d by length, the Coulombic potential will be dominating, and outside the d by length, your exponential decay term will start dominating. Okay. So this is some of the properties of the Coulombic potential. So now we have covered d by length. We know what is d by length, and we know what is the potential phi r inside the plasma. So this phi r is what? This phi r is the potential which is created due to the presence of test charge, which was introduced in the plasma. Okay. Now comes another topic which is called plasma frequency. Numerical comes on this. So from today's and tomorrow's class, because these are very important topics, number of numericals can be easy numericals, formula based numericals can be coming in the exam. I just hope, because these are important topics. Plasma frequency. So what is plasma frequency? So frequency comes whenever there is some sort of oscillation. We also did in atmospheric thermodynamics. We studied something on what was that? Some frequency we covered, right? Brunt-Weissela frequency. That is, if you displace a parcel from its mean position, depending upon the difference in the lapse rate, it may either be oscillate about its mean position or it will exponentially decay. Okay. So similarly, whenever there is some sort of oscillation about mean position, the frequency can come. So that suggests that when you're talking about plasma frequency, you're talking about the frequency of the electrons, basically, because ions are mostly static owing to their large mass. So it's basically electrons which move inside the plasma. So it is the frequency associated with the motion of electrons within the plasma. So suppose you displace electrons from the mean position to an E position. Number of electrons are there, you displace them some delta x, okay, distance. So earlier they were present at some initial position, say this position A. Now you have displaced it into by delta x amount to a new position called minus. So you form some sort of slab. Just imagine. So because you have displaced electrons, so after displacing electron, here positive charge will naturally appear because they are deficient of negative charge, so positive charge will come. Okay. So what is happening is that, let's make another slab. So what is happening, since you have displaced electrons from the mean position, an electric field will set up because there is some charge separation. You have created charge separation. This charge separation will set up an electric field. An electric field moves from positive plate to negative plate. Now this electric field will try and exert force such that the electron will move towards the positive plate. So electrons would try to move back to their original place. So that's the thing. So what happens is that when this electron try to, due to the electric field which is set up, when the electron try to move again back to the original place A, because they have certain mass, they will overshoot. They will overshoot their original position. Now this overshooting means that another electric field will be set up in this direction, second electric field, maybe E2. Now this E2 will again create a force in the opposite direction, so the electron again move back. So I am shading this with red. So electron motion is in red. So electron will again try to come back, and this purple one is electric field. Okay, so this is a kind of oscillation is created where electron is moving from one place to in one direction, then again it is moving again in another direction. So this charge separation leads to some oscillation, and the frequency associated with this oscillation of electrons is called plasma frequency. So let us derive this, the expression for that. So suppose this configuration is kind of parallel plate capacitor configuration, which we study in electrostatics and dynamics. Parallel plate capacitor. So in the parallel plate capacitor, the surface charge density this plate, for this electron plate, is sigma is equal to charge upon area, Q upon A, the area of the plate. Okay. Now this Q is what? Total charge. The total charge will be the charge density, that is per unit volume, and not times the charge per unit, that is E value, and delta X will also come, because we are talking about, because this has a charge density. Okay, so per unit volume, so volume times length will give you area. Okay, so that's why this del X term is coming, and negative sign is coming because your electron is negatively charged. Okay, so and also the electric field setup for this parallel plate configuration is given by sigma upon epsilon naught, surface charge density upon epsilon naught. Now sigma is what? Sigma is minus of E and not delta X on epsilon naught. Okay, so what will the force which will be exerted? So there will be some force also which will be exerting between these two plates, and that force is given by E times E. Now I'll just use Newton's law, second law. Which is equal to force is equal to ma. So when you get 3 and 4, we get because we'll substitute this into this, so we'll get minus E square and not delta X upon epsilon naught is equal to m times d2 del X by dt square. Okay, because del X is the amount, so let us write it del X. So it is amount which is displacement of the electron. This is how much the electrons are displaced. So we can write this further as double derivative of the displacement of the electron by dt square is equal to minus E square density del X upon m times epsilon naught. So this quantity can be further written as dt double derivative dt square is equal to minus omega p, plasma electron frequency, angular frequency del X. So this is your equation. Okay, this is how your general second order differential equation looks like for the harmonic oscillations. So the solution of this is harmonic, simple harmonic oscillations. For pendulum or even quantum mechanics, you must be encountering this kind of solutions. So this is a plasma frequency. So this coefficient of del X is called the plasma frequency. And why electron? Because generally ions are at rest inside plasma. It's electrons which are doing all the motion. So this is called the plasma frequency, and it is given as angular frequency. It is given as under root of E square, that is charge, times number density of electrons upon mass of electron and permittivity. So it's called the plasma frequency, but this is angular frequency because here 2 pi term is also there. So F frequency, general frequency is given by omega p by 2 pi. So it will be 1 upon 2 pi into E upon m naught upon m naught epsilon naught. We know epsilon naught value is some 8.85 into 10 power minus 12 some units, and mass of electron is what? It is what? 9 point some. Okay, so when you put all these values inside this, finally what you will get is the plasma frequency of electron is 9 times under root of charge density hertz, that is second inverse. So this is a very important formula. So easy questions will come, they will give you the charge density of electrons, and then it will ask you to find the frequency. They might also give other parameters like suppose there is some plasma at temperature T and at some charge density and naught and some other parameters, mass, some other thing, but you only need n naught. So your frequency is a function of under root of just density of electrons, number of electrons per unit volume. It doesn't depend upon temperature and all. It doesn't depend on temperature. So that's the frequency of plasma. Electron plasma frequency. So this is the frequency with which your electron will oscillate. Okay, this oscillation which is there will be with this frequency. So this is for the electrons, but suppose if they ask you what will be the frequency oscillations of other particles, so in that case you need to put in the value of the mass of that particle, because this I have just taken for the electrons. Suppose they are asking you is there some alpha particle which is 4 times mass of electron, or some other particle proton they make, then in that case you will have to put the value of m also. Keep it in mind that thing. Okay. Now comes another thing, another parameter which is called plasma parameter. It just means, what is plasma parameter? It means total number of electrons within the Debye sphere. So it will what? It will just, because inside the Debye sphere, if they are, we know charged number of density is Ne, that is, this is the amount of electrons per unit volume. So in total volume, you know the radius of the Debye sphere is lambda d, and radius of sphere is given by 4/3 pi r cube, where r is your Debye sphere length, which is lambda d cube. So they might also in assignment and all they ask you this kind of question. So this is the total number of electrons which are present within the Debye sphere. So this covers some of the initial things like Debye length, Debye potential, that is potential inside the plasma, and plasma frequency, and what is the plasma parameter. Plasma parameter is the plasma frequency, and these 4 points. Sorry, I missed the question. What is the question? What is the Debye length? What is it actually in short? Okay. Suppose you have some plasma. Plasma is collection of positive charge and negative charge. Now you introduce from outside, you put in some test charge which is positive q, some test charge you put which is positive. Now what will happen is that at t is equal to 0, due to this test charge we know that some potential will be set up which is given by q upon 4 pi epsilon naught, and due to this potential what will happen is that there will be also some Coulombic attraction, because this positive charge will start attracting the negative electrons which are there inside this plasma. So these negative electrons will start coming towards this positive discharge, and in doing so what they will do is that they will form a cloud. This is a characteristic of plasma. They will form a cloud or surrounding plasma, some type of circular cloud they will form. Okay. Now you may ask that and also because of the fact that the mass of electrons are very less than mass of ion, that means your velocity is larger. So that is why your electrons are very movable, so they can easily move inside the plasma and accumulate around this positive test charge. Now what will happen is that since it is a circular in shape, this circular shape is called Debye sphere. Of some, why Debye sphere? Because the radius of the sphere is lambda d, which is called Debye length. This is a characteristic of plasma. So what will happen is that outside this Debye length, suppose some negative charge is situated over here. So some negative charge is here. Now this negative charge will not feel the attractive force or Coulombic attraction of this positive charge. Because why? Because the potential up to this Debye length, because we have just derived the potential for the, it follows this form: 1 by 4 pi epsilon naught q upon r exponential minus r upon lambda. So up to for all the values of r less than Debye length, that is within the sphere, your all the negative electrons, some electrons would be inside also, okay, so those electrons will feel this Coulombic potential or Coulombic Coulombic potential. But outside this Debye sphere, this Coulombic, this term dominates, the exponential term dominates for large value of r. So outside this Debye sphere, the exponential term dominates. Therefore your potential, which initially was decaying as 1 by r, will start decaying exponentially. That is very strongly it will decay, and hence you can say that outside the Debye sphere the Coulombic potential is very weak, so no charge, negative charge, will feel the Coulombic interaction. So that is why it is called as the Debye sphere or Debye length. So it is a property of plasma inside. If you put a test charge outside, not inside plasma, then it will only have one kind of potential, which is electromagnetic potential, that q by r. So in that case V will tend to 0 only when r tends to infinity, but here V tends to 0 for r greater than lambda d. Okay, so that is a difference between that I think that is what Debye length is all about. And the expression of the Debye length is given by this derivation. Epsilon naught k by t upon e square n e. Somewhat clear? Hello? Okay, so I think I will move to next. So basically this is what it is, and this is the expression for the potential as well as the Debye length, Debye sphere. Now just give me 1 minute. I will talk about particle motion in electric and magnetic fields. Particle motions in electric and magnetic field. This is the next topic for today. It will take around 30 minutes for this, and after that next 30 minutes we will solve the questions related to all the topics which we covered this class and last class. Just give me 1 minute. Okay. So now, so now, what we understand is how the particle or these ions or electrons move inside electric field and magnetic field. Why we are trying to study these? Because you know that ionosphere consists of plasma, that is both electrons and ions. Okay. And also we have solar winds, which comes from sun. It also consists of plasma, that is electrons and high energetic particles and ions. Now these solar winds or ionosphere interacts with the magnetic field, which could be of Earth. Magnetic interacts with the magnetic field of Earth or Sun or anything, and also the electric field which is set up in the ionosphere. So we need to understand how the individual electrons and ions interacts with electric and magnetic field and how they move, or what is the equation of motion associated with these electrons and ions inside the electric and magnetic field. So there are, first of all, there are three descriptions. There are particle description for plasma. To describe the motion, there is first particle description. Second is fluid description. C is your statistical description. Okay. Now plasma shows up. Another point to note is that plasma shows a collective behavior, especially if it is very dense plasma, especially for dense plasma. However, for a low density plasma, low density means the number of particles, ions, electrons are not very high per unit volume. No, for low density plasma, the collective behavior means you can treat entire ions and electrons as one entity. It's not very important or not at all important. So in that case, we can treat electrons and ions as single particles. So for a low density plasma, there is no need to go through collective behavior. We can directly understand the motion by treating motion of plasma by treating electron and ion as single particle. So what you do is that you set up the equation of motion for a single electron or a single ion, and then you then you try to understand it for the entire system. So understanding the motion of a single electron and ion will give you a fair amount of knowledge of how the plasma is moving, or how the electrons and ions are moving within the plasma. So whatever plasma is there inside the solar wind, or whatever plasma is there in our ionosphere, they constantly interacts with the electric and magnetic field. We already told you that it constantly interacts with both the electric and the magnetic field. Okay. So first of all, it is important to understand the behavior of individual particles in the presence of electric field. Okay. So we'll try to understand the behavior. By behavior I mean velocity, trajectory, those things of electrons or ions in the presence of electric field and magnetic fields, different kind of electric and magnetic fields. After understanding the behavior, the same argument will apply will be applied for all the particles okay, what we call as plasmas. So you just need to set up the equation of motion for a single particle, and then same argument can be applied for all the particles, for all the parts. So it will summation for all the number of ions or number of electrons. So we will start with first of all something which is called as Lorentz force. So in the presence of electric and magnetic field, a charged particle such as electrons or ion will feel the electromagnetic force which is given by this formula, Lorentz force, which is given by F force experienced by particle is equal to the charge times electric field plus velocity of the particle v cross b. This is called Lorentz expression for force. This is Lorentz force. This is equation 1. We also know that the divergence from Maxwell equation, divergence of magnetic field is 0. That monopole doesn't exist, those things. And if from this we can define magnetic field as the curl of a vector potential, which is A. Okay. And substituting this vector potential, this is 2. And we also know from Maxwell equation, this is second Maxwell. We also know that the Maxwell equation is del cross E. Curl of the electric field is given by the negative rate of change of magnetic field. So from here we can put, so it will become curl of E is equal to minus del upon del T del cross E, or what it will become is curl of E plus del A by del T is equal to 0. Now from this equation you can write as, if anything of curl of anything is 0, so that that thing can be written as negative gradient of potential. So E plus, from mathematical physics course you will know that E plus del can be written as gradient of some potential phi. So basically your electric field becomes minus grad of phi minus, so this is your expression of magnetic field. Okay, wait, let it go. So it becomes This is the expression of electric field which positive charge or negative charge will experience when it is put in an electric and magnetic field. Okay, so this is a contribution from the magnetic field, and this is the extra term which is coming because of the presence of magnetic field. Now we'll move into more detail. So okay, so this is your electromagnetic force, but there are also another kind of force. So total force that a charge would experience in the presence of E and B is given by total force F total. I will write your electromagnetic force, which is Q Lorentz force, QE plus V cross B, plus a non-electromagnetic force which can be due to the mass, because your charge would also have certain amount of mass, and that mass would face gravitational force, suppose. So M times R. This is your electromagnetic force. This is your non-electromagnetic force, such as gravitational force. So in general, if you try to study suppose a particle to total force acting, so not only electromagnetic force exists in the presence of electromagnetic field, also some amount of gravitational force also exists if the particle has certain considerable amount of mass. So remember this. Okay, now we understand that if you take a charged particle and which is present inside ionosphere or solar wind, and you put it in its electric-magnetic field, it will face a Lorentz force. Okay, now we'll do a specific cases. Suppose the first case would be particle. We'll try to study the particle motion in presence of only a uniform and static electric field. So what does it mean? What does it mean? It means that suppose I will just draw the configuration. Suppose let me set up the coordinate system x, y, z. Coordinate system, this is your y, this is your z. Now suppose this is some medium which has some electric field which is put in the vertical direction, in the z direction, and magnetic field is 0. There is no magnetic field, and an electric field is present only in the z direction. That means it only has z component. This is your electric field. Okay, now what would happen is that magnetic field is 0. That means, and also the field is uniform By uniform it means it is homogeneous, that it doesn't vary in any direction, in the z direction, because it's only present in z direction. That means it is uniform in space. That means del E by del z is 0, and then also static in time. That is not changing with time. It's uniform in space and it's static in time. So both of the derivatives will go on 0. B is already 0. So what would be the equation of motion? So we know that the force due to the presence of electric field is given by charge times electric field. Well known formula. Okay, so this is equation 1. Now particle, suppose you have some particle which is, so this is about electric field and this is a force. So what force on what? So suppose there is some charge particle with mass q, charge q and mass m. It is moving into this medium. Okay, so this particle will face some force from this electric field. That force is QE. Now since particle also has some velocity, because the particle is in motion, with the velocity will have 3 components, so Vx I cap plus Vy j cap plus Vz k cap. Okay, this is the velocity of the particle. So we can write equation 1 as force is what? Mass time acceleration, which is the derivative of velocity with respect to time, is equal to q e z, because it is in z direction. Now this will become further d by dt Vx I cap plus Vy j cap plus. Okay, now we'll just equate both sides since there are no, so we'll just equate. So m dvx by dt is equal to 0. So that means if you integrate this, you will get some constant value, that is some initial velocity in the x direction. Similarly, secondly, you will equate the y component of the velocity with the, there is no y component of electric field, so it is 0. So that means if you integrate these equations, what you will get is Vy is equal to some constant, which is the initial velocity. And similarly, third is the, because the acceleration in the z direction, which is given by dv by dz by dt. Now since there is some electric field component in z direction, we will have certain value. Okay, when you integrate this, it will become dvz by dt is equal to qez by m. So when you integrate this, your vz will become some initial value plus q ez t upon m. So what does this signify? This signifies that if you have some charged particle which is coming in a region which has some electric field in the z direction, and the initial velocity of the particle is suppose v naught x, v naught y, v naught z. So what will happen is that since there is no electric field component in x direction and y direction, 0, and Ex is also 0, so there will be no acceleration in that direction. So the particle will keep on moving with initial velocity in that direction, and since only there is electric field present in the z direction, the particle motion will change in the z direction itself, and that too with linear change in time. So that is the change. So some initial velocity in the z direction plus q z into t by m. So what will happen is that, so what does it tell is that v and x is constant in time. They do not change, it changes linearly in time. it changes linearly in time. Okay. So what will happen is that if your charged particle is positive, suppose you have some plasma, so since it will move only in z direction, in initial velocity will be same, so it will face some acceleration in z direction. So suppose your electrons will move in the upward direction, and your electrons, owing to the charges q is negative for electrons, so electrons will move in negative direction, so some charge separation will be created. Overall your plasma is neutral, but due to the presence of electric uniform and static electric field, the charge separation will be created inside plasma, some local region inside plasma. Overall plasma will still be neutral, but it's still in some small packet inside the plasma. This charge separation will be created. Ions will move up and electrons will move down. Okay. So ions will move in the direction of electric field, and electrons will move opposite to the direction of electric field. Okay. So this is how we can understand the motion of particles inside. So it will be a linear motion, right? It will be a linear motion. Linear motion. So this is important. So the motion is linear when you have electron static fields. Second thing is, we have this Newton's second law equation, QE. So just take a dot product on both sides with V. So it will become m dv by dt times V is equal to Q E dot V. We can write this as for the d by dt of half m V square, right? 2 will cancel, m is constant, so m V will come out dv by dt. So same thing will get. Also E is also what? Minus gradient of phi. It will become. Now V is already we know is Vxi plus Vyj plus Vzk. Similarly, your gradient of phi can also be written as plus j cap del by del phi, or del by del x del by del y plus k cap del by del z times phi. So you just put this in these equations. Finally what you'll get is d by dt half mv square is equal to minus q, because v can also be written as dr by dt. So what you will get is minus q d phi by dt, because r will get cancelled, you will get d phi by dt. So, or in rearranging, you will get d by dt of half mv square plus 2 phi is 0. So something is conserved. This term in the bracket is what? Total energy, which is total energy of an electron or ion presence of electric field. Is constant, because derivative is 0, so it's constant. This is your kinetic energy, this is your potential energy. And also, since the total energy is conserved, that means the work done by electric field is 0 on particle is 0. So 3 important points. This is third point, this is second point. Total energy is conserved, work done by electric field and particle is 0, and charge will move linearly. Okay, so this is what it is done. Okay, so this is, and I will just write it here, linear motion of particle in the direction of, in or opposite to the direction of, if it is ion it will move in the direction, if it is not, if it is electron it will move opposite in direction. So linear motion. So these three are important points for a charge in uniform electric field. Okay. Now comes the second topic. Particle motion in a uniform and static magnetic field. So just replace electric with the magnetic field. So again we will set up the coordinate system. Now suppose instead of the electric field we put a magnetic field in this z direction. So magnetic field is what? And zero component in the x direction, zero component in the y direction, and in the z direction bz component. This is your magnetic field. And there is no electric field, there is only magnetic field present in some region. So here in this case your electric field is 0, and since it is uniform, so del B by del Z will be 0. Since it is static in time, so del V by del T will be 0. So the force, we know the force, magnetic force is given by when a charge particle with mass q and charge q with initial velocity v0x, v0y, v0z will approach this region of magnetic field, it will experience a force v cross v. So particle will feel the magnetic force only if it is moving. Particle at rest will not. Particle at rest would not feel magnetic force, but converse is not true for electric field. Electric field is q times E. Irrespective of the motion of the particle, if there is some electric field and some charged particle will always feel that force. But for magnetic force to be felt, the particle must also be in some motion. It should have some value of E. It should not be 0. Okay, important point to note. Another thing is that force which is acting on this, the force direction would be perpendicular to these V and B. So it will not be moving in the same direction. Unlike the electric field, the particle will moving in the same direction of the electric field. In this case, the particle move perpendicular to the plane which contains V and B. Okay, so that is an important point. And what would be the work done in this case? Let's derive the work done early only. So we know for work done is d by dt. We just take the Newton's second law and just take the derivative, write this as and dv by dt is equal to this. So from here we can write, take a dot product with v on both sides, we can write q v cross v dot v. What is this? Now this v cross v is perpendicular to v, and dot product of v with perpendicular to v, that means cos of 90, that will 0. So this term will be 0. So the work done will be 0. So we can just write this as d by dt of half mv square is equal to 0. So kinetic energy is conserved. That means it doesn't have any potential energy, it's only kinetic energy which is conserved. And the work done is 0. Work done is by magnetic field is also will be 0. Important point. First, second. These two are important points. Okay. Now, what would happen? Now let us derive the equation of motion for this particle. So we have this equation, right? So we can just write m times dv by dt is equal to q v cross v. What is v cross v? You can easily calculate this. Vx, vy, vz. Bx is 0, by is 0, bz, right? We only have z component. So when you calculate this, you only have z component. So it will become what? Q times I cap vy bz, okay, minus j cap vx bz plus k cap will be nothing. So this is what. So equation is, your equation becomes m d upon dt vx I cap plus vy j cap plus vz k cap is equal to q I cap vy bz minus q j cap vx bz. So when you equate term by term, what you'll get is m dvx by dt is equal to q times v by bz, and m dvy by dt to minus q vx bz. M derivative of velocity in z direction with respect to time will be 0. Okay, so there is no force in z direction. So magnetic field will not exert any force in the parallel in z direction or in direction parallel to magnetic field. It will only exert force in direction which is in the plane perpendicular to z, that is in dx and dy we will have some force. Okay. Okay, now let us derive the velocity expression in x and y direction. So from 1, you can write dvx by dt is equal to q upon m vy bz. Okay, and similarly we can write dvy by dt is equal to minus q by m vx times vz. These two equations in x and y component of velocity, and dvz by dt is 0 means vz will be constant. dvz by vz will be some constant value, which is the initial velocity of the particle in z direction. This vz naught or v o naught z is same only. Okay. Now if you solve this, what you can write? From B you can write dy by dt is minus qvx by vl. Okay. So when you integrate this, your vy will become minus q vx bz times t by m. Now use this into this equation, so it will become dvx by dt is equal to minus q square by m vx bz square t upon m square. So you can write this as dvx upon dt is equal to minus q square bz square right? Or if you take yeah, you can write this here. Yeah, vx q square bz square vx t upon m square. On differentiating this equation, it becomes d2 vx upon dt square is equal to minus q square bz square upon m square vx. Okay, this is one equation. Similarly for y we can write similarly. For y we can write d2 vy by dt square is equal to minus q square bz square vy upon m square. So these two are second order linear differential equation. So since it is very easy to know that some sort of oscillations will be there, because these are harmonic equations, and we know that d2 this is 0, d2 vz by dt square is equal to 0. So no force in acceleration z direction. So these equations represents the trajectory of the particle. So we can write this as further as, just suppose this is equation A, this is B, this is C. So if you take A, you can write it as d2 bx by dt square is equal to minus omega square times Vx. So where your Vx is, where your omega square is q square bz square by m, or omega is qb by, in general, qbz by m. So this is the angular frequency of the electron or ion when it is present in the presence of a uniform and static magnetic field. So it will start oscillating in a plane perpendicular to the direction which the magnetic field is applied with this frequency. We also know the solution of these equations A, B and C are nothing but the simple harmonic equation solution. Solution of equation A So since this equation solution is what? Vx can be written as, since it is oscillating, so in terms of sines and cosines we can write the oscillation. A cos omega t plus b sine, right? Now at t is equal to, we need to find what is A, what is B. Similarly, Vy is what? Vx is this, that is d, and Vy is what? Vy is we can write Vy as dvx by dt m by q by v. So Vy can be written as Vy can be written as, from this equation I would take, Vy can be written as m upon q bz dvx by dt. Now what is m upon q bz? This is 1 upon omega. So we'll just differentiate equation D. So it will become what? Minus A sine omega t. We'll just differentiating it times omega plus B omega cos omega t. This omega will cancel out. So your Vy is nothing but minus A sine omega t plus B cos E. So your next direction, it is this velocity, in y direction it is 1. Find what is A and B. We have to find A and B to get a complete picture. So we'll use initial conditions. So at t is equal to 0, your velocity at x was v naught x and velocity at y was v naught y. So we'll just use this in these two equations. Use in equation D and E. So we'll find out that v0x is equal to A cos of t, cos of 0 is 1, so A plus B sine of t, sine of 0 is 0. So your A is nothing but v naught x. Similarly, you put t is equal to 0 in the second equation, this E equation, so you'll get v naught y is equal to minus A times 0 plus B. So from here you get your B is equal to v naught y. So your B is equal to v naught y and your A is equal to v naught x, and your you just put this back in your original equations, these equations. So what we'll get is your Vx is V naught x cos of omega t plus V naught y sine of omega t. In the x direction, the velocity will be this. In the y direction, the velocity will be minus V naught x sine of omega t plus V naught y cos of omega t. And your Vz is what? Vz is constant because there is no force acting in the z direction in the plane perpendicular and parallel to the magnetic field. So it will be. So this is the equation, particle trajectory. A motion will be this, given by these equations. Okay. So now let us find the velocity, absolute magnitude of velocity. Magnitude. So it will be what? Square of under root of square of all the terms. So it will be V is equal to V square is equal to V naught x Vx square plus Vy square. Let us calculate first the velocity magnitude or in the xy direction where it is changing. It is where it is oscillating in the plane where it is oscillating. It is nothing but, you can also call this as the perpendicular velocity. Why? Because this is taking place in the plane xy plane, and xy plane is perpendicular to the z, which is the direction in which the magnetic field is applied. Okay, so it is nothing but, we will just take the square of both these terms. What we will get is V naught x square plus V naught y square. Now this is some sort of gives you circular motion, because you know the equation of circle is what? X square plus y square is some r square. So this gives us a hint that the particle will move, give a circular motion in the plane perpendicular to the magnetic field, circular motion. And the magnitude of that radius of that circle is given by under root of V naught x square plus Vy square. Similarly, we can also calculate from equation f and g, this is equation f, this is equation g. We can further integrate it to get the x and y coordinates. So dx by dt is V naught x cos of omega t plus V naught y sine of omega t, right? So we just integrate it. So what we'll get is x is equal to minus V naught x upon omega sine of omega t minus V naught y upon omega cos of omega t. Write it as h. Similarly, your dy, you can integrate for y and vy and get y is equal to V naught x cos of omega t upon omega plus V naught y of sine of omega t upon omega. So this is your x and y coordinates. So if you just take the square of both x square plus y square, because you want to find the radius of the circular path which the particle is performing in the plane perpendicular to the plane in which the magnetic field is applied. So it is what? And do this, it will come out to be V naught x square plus V naught y square upon omega square. And this is nothing but, this is what? V perpendicular square. So it will become V perpendicular square upon omega square. So this is something from, if you just equate with the equation of circle, just the square of the radius. The radius of circle is this. So the radius will be, I will just write it as radius, and this radius is what? V perpendicular upon omega, where omega is qb by m. So the particle will move in a circle with radius V perpendicular m times by qb in a plane xy plane which is perpendicular to the plane in which the field is applied. Okay, and yeah, so this is Vx, Vy, Vz. So okay, so the particle is moving. So let us see what would be the path of the particles. Okay, so in the z direction, in the z direction, particle is moving with a constant speed. So there is not that there is no motion in the z direction. It is moving, but with a constant speed. And also in the xy plane, it is moving. This is your x, y, z. So the particle is moving in constant speed in this z direction. Okay, and it's also moving in the xy plane. It is moving in circular. So the kind of motion it will have is some sort of. Let me draw it. So it will. So if you just draw it, motion x, y, z. So in xy plane it is moving in circle, in z direction moving constant speed. So your particle will be doing this kind of motion. So it is moving with a constant speed in z direction, plus is also moving in a circular path in vx and vy direction. So this is something which is called a helical path. So a particle in the presence of uniform static magnetic field will move in a helical path in the direction in which the magnetic field is applied. Okay, it will move with a constant speed in the direction in which magnetic field is applied, but it also performs circular motion in the xy plane. So that's why the resultant path is something which is called circular motion in xy plane plus constant velocity in z plane, in z direction, will give you something which is called helical path. Right? So this is how the particle will move. Now a few things to remember for this helical path. Now few terms. First term is the frequency with which the particle is moving, which is omega, is called the cyclotron frequency. Cyclotron. And angular frequency is omega c is what? QB by m. Charge times magnetic field times m. So cyclotron frequency, which is in not radian per second but just second inverse, is omega c by 2 pi, which is QB upon 2 pi m. So this is the frequency with which the particle in hertz. So this is provided you take all the units in standard units of all the parameters. So this is the frequency with which the particle will cyclotron frequency. Okay. And the third thing is the radius of gyration. So this motion is helical path which the particle is doing in the magnetic field is called. This motion is called radius of gyration, and radius with which it is moving in xy plane, that radius is called radius of gyration, and that is given by r is equal to mv perpendicular upon qb, where v perpendicular is called v naught x square plus v naught x square. Okay. A few things to notice is that your r is directly proportional to the mass of the particle, and since the mass of ion is greater than mass of electron, the radius of gyration of electron will always be greater than radius of gyration of ion will always greater than radius of gyration of electron. So for example, if you have some magnetic field in z direction, so your ions will move in this direction, say suppose they will gyrate around this, and your electrons They will also move in the opposite direction. It is going in the clockwise. They will move in anti-clockwise, and they will move very small. Why? Because the radius of this helical path is very smaller, and this radius of the helical path is larger. So that things need to be mind. The radius of gyration of ions is always greater than the radius of gyration of electrons. And also, so this is one thing. So these are three important terms when it comes to solving questions, numericals. Okay, so I'll just quickly solve few of the numericals which was there in the a lot of topic today. Okay, so let's move to the first question, the assignment. So according to the theory of peak production at any height, the product of the number of molecules in cross-sectional area should be what? So we did in the Chapman's theory that the peak production happens when the total number of particles inside the volume is equal to the inverse of the cross-sectional area. So this signifies that m times sigma is equal to 1. So for this is one of the assumptions, so this terms right. The height of the peat production in ionosphere is independent of, so we derived that the height of the peat production given by Hm is equal to h times natural log of the area of cross section times density times the scale height of the atmosphere or the ionosphere times sec of zenith angle, the angle which is making from the normal. So it is independent of incident radiation. So cross sectional area is there, density is there, zenith angle is there, scale height is there. So first option not, this is right. Solar zenith angle, no, it depends upon, so only this option, it doesn't depend on incident radiation. According to Chapman's theory, the height of peat production decreases as height of peat production is directly proportional to the sec of chi. So as chi decreases, your sec of chi also decrease and your Hm will also decrease. The height of production decreases as your chi decreases. So this is the right option. Now the scale height for hydrogen atom at a temperature at 300 Kelvin will be given by what? So what is scale height? So scale height is given by this formula. We know that it's given by R dt by G for dry atmosphere. But suppose this dry atmosphere is all oxygen, nitrogen, everything. But suppose this atmosphere only contains a hydrogen atom. In that case, your scale height will be R star upon mass of hydrogen atoms times T upon G. So when you solve this, all the values, you will put 8.314 joules per mole per Kelvin times temperature is 300. The mass of hydrogen is 1 gram times 9.8. What you will get is 254.51 kilometers. Now, in general atmosphere, we know that scale height in a dry atmosphere is around 7 to 8 kilometers. So suppose if your atmosphere has only hydrogen atom, then the scale height of the atmosphere would be number of times 254 divided by 7 is 36 times larger than what today's. That means that what does scale height signifies? That most of the atmosphere is concentrated, mass of the atmosphere is in lower part, but below 7 to 8 kilometers. It drops significantly from 7 to 8 kilometers, 1 by 8 times. Now in the atmosphere, only a hydrogen atom that suggests that the mass would not be concentrated near the Earth's surface. Okay, so the mass of the atmosphere would drop to 1 by E times, only drop to 1 by E times, only at a scale height of 254 kilometers. Okay, when it will run 254 kilometers, then it will become rho naught by E. So that is important. Now fifth question, which of the following are not criteria for plasma inside a dBi sphere, where Nd is the number of particles in dBi sphere, T is the mean oscillation time, and lambda is a dBi length, omega is the frequency of plasma. Now we know that inside the dBi sphere, the number of particle should be greater than 1, so this is true. Omega t is greater than equal to 1, so where omega is the frequency, plasma frequency. So when we derive the frequency of plasma, so that term, that frequency is sometimes 9 times 1. So this cannot be less than 1. So this is always greater than 1. So this the product actually, this, when you just solve this, omega p is 2 pi times this frequency times c. This should always be greater than 1. Okay. Although we have not done this derivation, but keep it in mind. The third term is because straight away, even if you don't know the second logic, you can easily say that this is wrong, because lambda is Debye length has a dimension of length, where omega t, where omega is it has unit of radian per second inverse per second, and time as a unit of second. So it is unitless, kind of unitless. So how you can compare it with something which is unit length? So this is wrong. This is wrong comparison. So fifth one is wrong. Debye shielding will be perfect in the plasma. So what happens? So if you put a test charge, electron starts accumulating around this test charge. But why does this electron doesn't stick to this positive charge? This is because electrons have certain amount of temperature. They exist at certain amount of temperature. That's why they have certain amount of kinetic energy, which this kinetic and thermal kinetic energy takes the electron away from this positive. Coulombic energy is attracting, thermal energy is repelling. So if there is no temperature, if there is no thermal motion, ideally T is 0, no thermal energy, then all these electrons due to Coulombic interaction will completely stick to this positive charge, completely nullifying it and giving the perfect shielding. So the shielding will be perfect in the plasma if there is no thermal motion, no thermal energy. Okay. Find the Debye length of the charge density. So you have to find, you just use the formula of the Debye length. So the formula is epsilon kBt upon n times E square. Now K is what? This will be given in question paper 8.85 in 10 power minus 12. kBt is given as 0.1 electron volt, and 1 electron volt has 1.6 into 10 to the power minus 19 joule of energy. Okay. Divided by number density is 10 to the power 12. So this is basically somewhere at the when the peak density in ionosphere. Peak density in ionosphere is 10 to the power 12. So that region, it's they are asking to calculate Debye length times. So when you just calculate this thing, okay, finally what you'll get is 2.35 into 10 to the power minus 3 meter. So see, the Debye length for is very, very small. Okay, it's around 2.35 into 10 to the power minus 3. This is the right answer. So after this length dimension in the sphere with the radius of this Debye length, the particles, the test charge will exert its dominance, or this potential will be felt outside the Debye sphere. It will be shielded. This positive test charge will be shielded, and its impact will not be felt by particle outside the Debye sphere. In a laser fusion, the small pellet is compressed to density of 10 to the power 26 meter per cube at a temperature of 15 to 10 power 6 Kelvin. The number of particles in the Debye sphere is what? So this is Debye parameter. Number of particles in what? Sphere is, volume of the sphere is 4 by 3 pi lambda d cube. So this is the volume of the Debye sphere times the number of particles density, which is 10 to the power 26. So again put this value again here, lambda d, you will use this formula. So it will become 4 by 3 pi epsilon naught kBt upon n E square to the power 3 by 2 into 10 to the power 26. You know epsilon, you know kb. Kb is what? Kb is 1.38 into 10 to the power minus 23. You can confirm this value. T is given 15 to 10 to the power 6 Kelvin. N is given 10 to the power 26 meter cube. E is what? 1.6 into 10 to the power minus 19 coulomb. Using all this value, you can just find. It will come out to be 4.8. For me, it has come out to 4.828 into 10 to the power 4 particles. So A. So these amount of particles are present within the Debye sphere. Now, 8th question. In a laser fusion, the core of a small pellet is okay, this is already done. Calculate the plasma frequency for electron plasma if the electron density is this. The plasma frequency we already know is given by 9 times under root of the density. So 9 times under root of the electron density, which is 4 into 10 to the power 10. So what? 18 into 10 to the power 5 hertz, or 1.8 megahertz. So this is the density of the electron plasma. So this is the plasma frequency if the electron density is this 4 into 10 to the power 10. Last question is, what is the value of electric potential in Debye sphere? The value of the electric potential in the Debye sphere, you already know. It has a Coulombic part which goes as 1 by 4 pi epsilon naught q by r, and it has a exponential part which goes as this. So here they have written this as phi naught, which is Coulombic part, times exponential minus lambda d. This is the right option. Okay, so this is the value of electric potential for the Debye sphere. Okay, so I think I've solved all the questions. Few of the other questions related to the radius of gyration and all will be solved in the next tomorrow class, and then I will just cover the last topic, which is curvature drift and auroras and those air glow, mirror, electron mirroring, those things. Okay, so thank you for today's class. I will end today's class now. Thank you.